Oops, sorry, I was muted. Hello and welcome to the third live stream in the Stanford NLP with Deep Learning series. My name is Tushar Thamani. Thank you for joining. In the past two lectures, we've basically started off with what is NLP and then word to vec algorithm. Yesterday we ended off with a little bit of a deeper perspective of what that is and how do we get to the optimization point of view in the application. I did find, as I had earlier mentioned, the course materials and the exercise codes. I have in the description linked the course playlist. So under the playlist you see that link. I'll just show you where it is, what it is. Yep, so this is the I have these playlist links, so wherever you go, on whichever video you are, if you look in the description, you'll find the link to come to this page, but there is the course schedule and syllabus. If you click on that, I link this particular page as well in the description, so you'll find slides and everything to review if you want to, but I just quickly wanted to jump into okay, so we also have assignment code which will be good to practice. Okay, I think we can do like an exercise video that will help us get a better understanding. I believe this is okay. This was submission. Assuming, yeah. So there are examples for the vector. I think question that was, yeah, this was the one that was discussed in the class. Okay, yeah, we can do both, or what we can do is we can do the exercise and then if you want you can try the assignment questions and then I'll try them on my own dime and we can discuss later on. But okay, so lecture number 3, without further ado, let's begin.
Okay, hi everyone. Okay, let's get started. Great to see you all here. Welcome back for week 2 of CS224N. So this is a little preview of what's coming up in the class for this week and next week. You know, this week is perhaps the worst week of this class. So in week 2 of the class, our hope is to actually kind of go through some of the nitty-gritty of neural networks and how they're trained and how we can learn good neural networks by backpropagation, which means in particular we're going to be sort of talking about the training algorithms and doing calculus to work out gradients for improving them. So we'll look a little bit at word window classification, named entity recognition. So there's a teeny bit of natural language processing in there, but basically sort of week 2 is sort of math of deep learning and neural network models and sort of really neural network fundamentals. But the hope is that that will give you kind of a good understanding of how these things really work and will give you all the information you need to do the coming up homework. And so then in week 3, we kind of flip. So then week 3 is going to be mainly about natural language processing. So we're then going to talk about how to put syntactic structures over sentences for building dependency parsers of sentences, which is then actually what's used in homework 3. So we're chugging along rapidly. And then we'll talk about this idea of the probability of a sentence, which leads into neural language models. So on the homeworks, homework 1 was due approximately 2 minutes ago. So I hope everyone has submitted their homework 1. I mean, as one just sort of admonition, in general, it's sort homework 1 we hope you found was a good warm-up and not too hard, and so it'd really be best to get homework 1 in quickly rather than to burn lots of your late days doing homework 1. And now, right now, out on the website, there's homework 2, so we're chugging along. So homework 2 kind of corresponds to this week's lectures. So in the first part of it, we're expecting you to grind through some math problems of working out gradient derivations. And then the second part of it is then implementing your own version of Word2Vec, making use of NumPy. And so this time sort of writing a Python program. It's no longer an IPython notebook. Encourage you to get early, look at the materials on the web. I mean, in particular, corresponding to today's lecture, there's some quite good tutorial materials that are available on the website, and so also encourage you to look at those. More generally, just to make a couple more comments on things, I mean, I guess this is true of a lot of classes at Stanford, but when we get the course reviews for this class, we always get the full spectrum, from people who say the class is terrible and it's way too much work, to people who say it's a really great class, one of their favorite classes at Stanford, obviously instructors care, etc. And I mean, partly this reflects that we get this very wide range of people coming to take this class. So on the one hand, on the right-hand margin, perhaps we have the physics PhDs, and on the left-hand margin, we have some frosh who think this will be fun to do anyway. We welcome everybody, but in principle, this is a graduate-level class. That doesn't mean we want to fail people out. We'd like everyone to succeed, but also, like graduate level class, we'd like you to, take some initiative in your success, meaning if there are things that you need to know to do the assignments and you don't know them, then you should be taking some initiative to find some tutorials, come to office hours and talk to people and get any help you need and learn to sort of for any holes in your knowledge. Okay, so here's the plan for today. So that was the course information update. So, this is sort of, in some sense, machine learning neural nets intro, just to try and make sure everyone is up to speed on all of this stuff. So talk a little bit about classification, introduce neural networks, little detour into named entity recognition, then sort of show a model of doing word window classification, and then at the end part we sort of then dive deeper into what kind of tools we need to learn neural networks. And so today we're going to go through somewhere between review and primer of matrix calculus, and then that will lead into next time's lecture where it's talking more about backpropagation and computation graphs. So this material, especially the part at the end, for some people it'll seem really babyish if it's the kind of stuff you do every week. For other people, it might seem impossibly difficult, but hopefully for a large percentage of you in the middle, this will be kind of a useful review of doing this kind of matrix calculus and the kind of things that we hope that you can do on homework 2. Okay, so so sorry if I'm boring some people. If you sat through 229 last quarter, you saw what a classifier was like, and hopefully this will seem familiar, but I'm just sort of hoping to try and have everyone in week 2 sort of up to speed and on roughly the same page. So here's our classification setup. So we assume we have a training data set where we have these vector x of our x points, and then for each of one of them we have a class. So the inputs might be words or sentences, documents or something. They're a d-dimensional vector. The yi are the labels or classes that we want to classify to, and we've got a set of C classes that we're trying to predict. And so those might be something like the topic of a document, the sentiment, positive or negative, of a document, or later we'll look a bit more at named entities. Okay, so if we have that, for this sort of intuition is we've got this vector space of which we again have a 2D picture, and we have points in that vector space which correspond to our x items, and what we'd want to do is look at the ones in our training sample and see which ones are green and red for our two classes here, and then we want to sort of learn a line that could divide between the green and the red ones as best as possible, and that learned line is our classifier. So in traditional machine learning or statistics, we have the sort of xi vectors are our data items that are purely fixed, but we're going to then multiply those xi by some estimated weight vector, and that estimated weight vector will then go into a classification decision. And the classifier that I'm showing here is a softmax classifier, which is almost identical but not quite to a logistic regression classifier, which you should have seen in CS 109 or a stats class or something like that, which is giving a probability of different classes. Okay, and in particular, if you've got a softmax classifier or a logistic regression classifier, these are what are called linear classifiers. So the decision boundary between two classes here is a line in some suitably high-dimensional space. So it's a plane or a hyperplane once you've got a bigger x vector. Okay, so here's our softmax classifier, and there are sort of two parts to that. So in the weight matrix W, we have a row corresponding to each class, and then for that row, we're sort of dot producting it with our data point vector xi, and that's giving us a kind of a score for how likely it is that the example belongs to that class. And then we're running that through a softmax function, and just as we saw in week 1, this softmax takes a bunch of numbers and turns them into a probability distribution. Does that make sense to people? People remember that from last week? Good so far? Okay, I'm not going to go to this in detail, but I mean, essentially, this is what a logistic regression does as well. The difference is that here in this setup, we have a weight vector for each class, whereas what the statisticians do in logistic regression is they say, wait, that gives us one more number of weight vectors than we really need. We can get away, for C classes, we can get away with C-1 weight vectors. So in particular, if you're doing binary logistic regression, you only need one weight vector, whereas this softmax regression formulation, you've actually got two weight vectors, one for each class. So there's that sort of little difference there, which we could get into, but basically the same. Let's just say we're either doing softmax or logistic regression, doesn't matter. So when we're training, what we want to do is we want to be able to predict the correct class. And so the way we're going to do that is we're going to want to train our model so it gives as high as probability as possible to the correct class, and therefore it'll give as low a probability as possible to the wrong classes. And so our criterion for doing that is we're going to create this negative log probability of our assignments, and then we're going to want to minimize the negative log probability, which corresponds to maximizing the log probability, which corresponds to maximizing the probability. Sort of pretty soon now we're going to start doing more stuff with deep learning frameworks. in particular PyTorch, and you can discover in that there's actually a thing called NLL loss, which stands for negative log likelihood loss. But basically no one uses it because the more convenient thing to use is what's called the cross-entropy loss. And so you'll hear everywhere that we're training with cross-entropy loss. So I just wanted to briefly mention that and explain what's going on there. So the concept of cross-entropy comes from...
Sorry, I missed this. So we're minimizing the negative log probability. Okay, I think this is the similar stuff we looked in the earlier classes. Sorry, I just missed that. To add to my notes, summation, yeah, it's the same. Exponential function C. Okay. Let's move on.
With cross-entropy loss. So I just wanted to briefly mention that and explain what's going on there. So the concept of cross-entropy comes from baby information theory, which is about the amount of information theory I know. So we're assuming that there's some true probability distribution P, and our model, we've built some probability distribution Q. That's what we've built with our softmax regression. And we want to have a measure of whether our estimated probability distribution is a good one. And the way we do it in cross-entropy is we go through the classes and we say, what's the probability of the class according to the true model? Using that weighting, we then work out the log of the probability according to our estimated model, and we sum those up and negate it, and that is our cross-entropy measure. Okay, so this in general gives you a measure of sort of information between distributions, but in our particular case, remember that for each example, we've sort of assuming that this is a piece of labeled training data. So we're saying for that example, the right answer is class 7. So therefore, our true distribution, our P, is, for this example, it's class 7 with probability 1, and it's class anything else with probability 0. So if you think about then what happens with this formula, you've got this summation over all the classes, but P of C is going to be either 1 or 0, and it's going to be 1 only for the true class here. And so what you're left with is this is going to equal minus the log of QC for the true class, which is sort of what we were then computing in the previous slide. Okay, so that's what... yeah, so that's basically where you get with cross-entropy loss. But one other concept to mention, so when you have a full data set of a whole bunch of examples, the cross-entropy loss is then taking the per example average. So I guess it's what information theory people sometimes call the cross-entropy rate. So additionally factored in there, if you're training it on n examples, there's that 1 on n factor that's coming in there. Okay. Okay. So that's cross-entropy loss. Is that okay? Yeah.
Or there's some mixture of the actual labels in the graph.
Sure. Good question. Right. So the simplest case is that your goal data, someone has hand labeled it, and they've labeled 1 and the rest is 0. You can think of cases where that isn't the case. I mean, one case is you could believe that human beings sometimes don't know the right answer. So if human beings said, I'm not sure whether this should be class 3 or 4, you could imagine that we can make training data where we put probability half on both of them. And that wouldn't be a crazy thing to do. And so then you'd, have a true cross-entropy loss using more of a distribution. The case where it's much more commonly used in actual practice is there are many circumstances in which people want to do semi-supervised learning. So I guess this is a topic that both my group and Chris Ray's group have worked on quite a lot, where we don't actually have fully labeled data, but we've got some means of guessing what the labels of the data are. And if we're trying to guess labels of data, well then quite often we'll say, here's this data item, it's 2/3 chance it's this label, but it could be these other 4 labels, and we'd use a probability distribution, and yeah, then it's more general cross-entropy loss. Okay. Right, so that's cross-entropy loss we're good with. This bottom bit's a little bit different, which is to say, well, now this is the sort of the full data set. The other thing to notice when we have a full, that we can have a full data set of x's, and then we have a full set of weights, where here we're working a row vector for the weights for one class, but we're going to work it out for all classes. So we can sort of simplify what we're writing here, and we can sort of use matrix notation and just work directly in terms of the matrix W. Okay, so for traditional ML optimization, our parameters are these sets of weights for the different classes. So for each of the classes, we have a d-dimensional row vector of weights, because we're going to sort of dot product with our d-dimensional input vector. So we have c times d items in our W matrix, and those are the parameters of our model. And so if we want to learn that model using the ideas of gradient descent, stochastic gradient descent, we're going to do sort of what we started to talk about last time. We have these set of parameters, we work out the gradient, the partial derivatives of all of these, of the loss with respect to all of these parameters, and we use that to get a gradient update on our loss function, and we move around the W's, and moving around the W's corresponds to sort of moving this line that separates between the classes, and we fiddle that around so as to minimize our loss, which corresponds to choosing a line that best separates between the items of the classes in some sense. Okay, so that's a basic classifier. So the first question
okay, so we will update the decision boundary gradient. Okay. I think it's fine.
loss, which corresponds to choosing a line that best separates between the items of the classes in some sense. Okay, so that's a basic classifier. So the first question is, well, how are things going to be different with a neural network classifier? And so the essential observation is that sort of most of the classic classifiers that people used a lot of the time, so that includes things like naive Bayes models, basic support vector machines, softmax or logistic regressions, they're sort of fairly simple classifiers. In particular, those are all linear classifiers, which are going to classify by drawing a line, or in the higher dimensional space by drawing some kind of plane that separates examples. And having a simple classifier like that can be useful in certain circumstances. I mean, that gives you what in machine learning is a high bias classifier, as there's lots of talk of in CS229. But if you have a data set that's like this, you can't do a very good job at classifying all the points correctly if you have a high bias classifier, because you can only draw a line. So you'd like to have a more powerful classifier. And essentially, what's been powering a lot of the use of deep learning is that in a lot of cases, when you have natural signals, so those are things like speech, language, images, and things like that. You have a ton of data, so you could learn a quite sophisticated classifier, but representing the classes in terms of the input data is sort of very complex. You could never do it by just drawing a line between the two classes. And so you'd like to use some more complicated kind of classifier. And so neural networks, the multi-layer neural networks that we're going to be starting to get into now, precisely what they do is provide you a way to learn very complex, almost limitly complex, in fact, classifiers, so that if you look at the decisions that they're making in terms of the original space, they can be learning cases like this. I put the pointer on a couple of the slides here. This is a visualization that was done by Andre Karpathy, who was a PhD student here until a couple of years ago. So this is a little JavaScript app that you can find off his website, and it's actually a lot of fun to play with to see what kind of decision boundaries you can get a neural net to come up with. Okay, so for getting more advanced classification out of a neural net used for natural language, there are sort of two things that you can do that I want to talk about, which are in some sense the same thing when it comes down to it, but I'll sort of mention them separately at the beginning. That one of them is that we have these word vectors. And then the second one is that we're going to build deeper multi-layer networks. Okay, so a first crucial difference that we already started to see with what we were doing last week is rather than sort of having a word being this is the word house, we instead say house is a vector of real numbers, and what we can do is change the vector that corresponds to house in such a way as we can build better classifiers, which means that we're going to be sort of moving house's representation around the space to capture things that we're interested in, like word similarity, analogies, and things like that. So this is actually, kind of a weird idea compared to conventional stats or ML. So rather than saying we just have the parameters W, we also say that all of these word representations are also parameters of our model. So we're actually going to change the representations of words to allow our classifiers to do better. So we're simultaneously changing the weights and we're changing the representation of words, and we're optimizing both of them at once to try and make our model as good as possible. And so this is the sense in which people often talk about for deep learning models, that we're doing representation learning. Right, I sort of said there are two ways. I was going to mention two things. One's this sort of word vector representation learning, and then the second one is that we're going to start looking at deeper multi-layer neural networks. Sort of hidden over here on the slide is the observation that really you can think of word vector embedding as just having a model with one more neural network layer. So if you imagine that each word was a one hot vector for the different word types in your model, so you had a 150,000 dimensional vector with the sort of one hot encoding of different words, then you could say you have a matrix L, which is sort of your lexicon matrix, and you will pass your one hot vector for a word through a layer of neural net which multiplies the one hot vector, or L and the one hot vector. And since this is a one hot vector, what that will have the effect of doing is taking out a column of L. And so really we've got an extra layer of matrix in our neural net, and we're learning the parameters of that matrix in the same way as we're learning a deep neural network for other purposes. So mathematically, that completely makes sense, and that's sort of a sensible way to think about what you're doing with word embeddings in neural networks. Implementation-wise, this makes no sense at all, and no one does this because it just doesn't make sense to do a matrix multiply when the result of the matrix multiply will be, okay, this is word ID 17, sort of then constructing a one-hot vector of length 150,000 with a 1 in position 17 and then doing a matrix multiply makes no sense. You just take out column or the row, as we've discussed, 17 of your matrix, and that's what everyone actually does. Okay. Here's my one obligatory picture of neurons for the class. So don't miss it. I'm not going to show it again, all class. Okay, so the origins of neural networks was in some sense to try and construct an artificial neuron that seemed to in some sense kind of capture the kind of computations.
I just
that
have
go
to go
on.
back and look at one thing.
Yeah.
Are we... Okay. Large number of parameters, okay. Yep.
You know, our model here is this is a teeny part of our human brain. So here are our neurons. This is a neuron cell here. And so what does a neuron consist of? So up the back, it's got these dendrites, lots of dendrites. Then it's got a cell body. And if there's stuff coming in on the dendrites, the cell body will become active, and then it'll start spiking down this long thing which is called the axon. And so then these axons lead to the dendrites of a different cell, or lots of different cells, right? This one, I'm not sure it's shown, but some of these are kind of going to different cells. And so you then have these sort of terminal buttons on the axon, which are kind of close to the dendrites but have a little gap in them, and some miracles of biochemistry happen there. And so that's the synapse across which you'll then have sort of activation flowing, which goes into the next neuron. So that was the starting off model that people wanted to try and simulate in computation. So people came up with this model of an artificial neuron, so that we have things coming in from other neurons at some level of activation. So that's a number x0, x1, x2. Then synapses vary depending on how excitable they are as to how easily they'll let signal cross across the synapse. And so that's being modeled by multiplying them by a weight, W0, W1, W2. And then the cell body, sort of correctly, is sort of summing this amount of excitation it's getting from the different dendrites, and then it can have its own bias as to how likely it is to fire. That's the B. So we get that, and then it has some overall kind of threshold or propensity for firing, so we sort of stick it through an activation function, which sort of will determine a firing rate, and that will be the signal that's going out on the output axon. So that was sort of the starting point of that. But, you know, really, for what we've ended up computing, we just have a little bit of baby math here, which actually looks very familiar to the kind of baby math you see in linear algebra and statistics, and so it's really no different. So in particular, a neuron can very easily be a binary logistic regression unit, so that this is sort of, for a logistic regression, you're taking for your input x, you're multiplying it by a weight vector, you're adding your bias term, and then you're putting it through a nonlinearity like the logistic function, and then So you're calculating a logistic regression inside this sort of neuron model. And so this is the difference between the softmax and the logistic regression, as I was saying, that whereas the softmax for two classes has two sets of parameters, this sort of just has one set of parameters z, and you're modeling the two classes by giving the probability of one class from 0 to 1, depending on whether the input to the logistic regression is highly negative or highly positive. Okay, so really we can just say these artificial neurons are sort of like binary logistic regression units, or we can make variants of binary logistic regression units by using some different f function, and we'll come back to that again pretty soon. Okay, well, so that gives us one neuron. So one neuron is a logistic regression unit for current purposes. So crucially, what we're wanting to do with neural networks is say, well, why only run one logistic regression? Why don't we run a whole bunch of logistic regressions at the same time? So, here are our inputs, and here's our little logistic regression unit, but we could run 3 logistic regressions at the same time, or we could run any number of them. Well, that's good, but sort of for conventional training of a statistical model, we'd sort of have to determine for those orange outputs of the logistic regression, what we're training each of them to try and capture. We'd have to have data to predict what they're going to try and capture. And so the secret of sort of then building bigger neural networks is to say, we don't actually want to decide ahead of time what those little orange logistic regressions are trying to capture. We want the neural network to self-organize so that those orange logistic regression units learn something useful. And well, what is something useful? Well, our idea is to say we do actually have some tasks that we want to do. So we have some tasks that we want to do. So maybe we want to sort of decide whether a movie review is positive or negative, something like sentiment analysis or something like that. So there is something we want to do at the end of the day. And we're going to have a logistic regression classifier there telling us positive or negative. But the inputs to that aren't going to directly be something like words in the document. They're going to be this intermediate layer of logistic regression units. And we're going to train this whole thing to minimize our cross-entropy loss. And essentially what we're going to want to have happen, and the backpropagation algorithm will do for us, is to say, you things in the middle, it's your job to find some useful way to calculate values from the underlying data such that it'll help our final classifier make a good decision. And I mean, in particular, back to this picture, the final classifier, it's just a linear classifier, a softmax or a logistic regression. It's going to have a line like this. But if the intermediate classifiers, they are like a word embedding, they can kind of sort of re-represent the space and shift things around. So they can learn to shift things around in such a way as you're learning a highly nonlinear function of the original input space. Okay. And so at that point, it's simply a matter of saying, well, why stop there? Maybe it'd get even better if we put in more layers, and this sort of gets us into the area of deep learning. And sort of precisely, this is that sort of there's sort of been 3 comings of neural networks. There was the first work in the 50s, which is essentially when people had a model of a single neuron like this, and then only gradually worked out how it related to more conventional statistics. Then there was the second version of neural networks, which was sort of the 80s and early 90s, where people built neural networks like this that had this one hidden layer where a representation could be learned in the middle. But at that time, it really wasn't effective or people weren't able to build deeper networks and get them to do anything useful. So you sort of had these neural networks with one hidden layers. And so precisely with research that started into deep learning, that precisely the motivating question is, we believe we'll be able to do even more sophisticated classification for more complex tasks, things like speech recognition and image recognition, if we could have a deeper network which will be able to more effectively learn more sophisticated functions of the input, which will allow us to do things like recognize sounds of a language. How could we possibly train such a network so that it works effectively? And that's the kind of thing we'll go on to more so, starting this lecture, more so in the next lecture. But before we get to there, just to underline it again, so once we have something like this as our layer of a neural network, we have a vector of inputs, we have a vector of outputs, and everything is connected so that we've got this sort of weights along every one of these black lines. And so we can say A1 is you're taking weights times each component of x1 and adding a bias term, and then you're going to be running, which is sort of this part, and then running it through our nonlinearity, and that will give us an output. And we're going to do that for each of A1, A2, and A3. So again, we can kind of regard A as a vector, and we can kind of collapse it into this matrix notation for working out the effects of layers. So fully connected layers are effectively matrices of weights. And commonly we write them like this, where we have the bias term as a vector of bias terms. There's sort of a choice there. You can either have an always-on input, and then the bias terms become part of the weights of a slightly bigger matrix with one extra either column or row. One extra row, right? Or you can just sort of have them separately written as B's. Okay. And then the final note here, right, so once we've calculated this part, we always put things through nonlinearity, which is referred to as the activation function. And so something like the logistic transform I showed earlier is an activation function. And this is written as sort of vector input, activation function, giving a vector output. And what this always means is that we apply this function element-wise. So we're applying the logistic function, which is sort of naturally a one input, one output function, like the little graph I showed before. So when we apply that to a vector, we apply it to each element of the vector element-wise. Okay. We will come back very soon to sort of saying more about nonlinearities and what nonlinearities people actually use. But, you know, something you might be wondering is, well, why does he always have these nonlinearities and say there has to be an f function there? You know, why don't we just calculate z equals wx plus b in one layer and then go on to another layer that also does z2 equals w2, z1 plus b, and keep on going with layers like that. And there's a very precise reason for that, which is if you want to have a neural network learn anything interesting, you have to stick in some function f, which is a nonlinear function, such as the logistic curve I showed before. And the reason for that is that if you're sort of doing linear transforms like wx plus b and then w2 z1 plus b, w3 z2 plus b, and you're doing a sequence of linear transforms, well, multiple linear transforms just compose to become a linear transform, right? So one linear transform is rotating and stretching the space somehow, and you can rotate and stretch the space again, but the result of that is just one bigger rotate and stretch of the space. So you don't get any extra power for a classifier by simply having multiple linear transforms. But as soon as you stick in almost any kind of non-linearity, then you get additional power. And so, you know, for in general, what we're doing when we're doing deep networks, in the middle of them, we're not thinking, oh, it's really important to have non-linearity, thinking about probabilities or something like that. Our general picture is, well, we want to be able to do effective function approximation or curve fitting. We'd like to learn a space like this, and we can only do that if we're sort of putting in some non-linearities which allow us to learn these kind of curvy decision patterns. And so sort of F is used effectively for doing accurate function approximation or sort of pattern matching as you go along. Okay. I think I'm behind already. Okay. So that was the intro to baby neural.
Let's take a break for a few minutes because I think NER would be a heavy topic in itself. I'll be back in 2 or 3 minutes. Okay. We are back, and something happened to my OBS. Give me 1 second, let me fix this. I think it's reconnected or something, but I'm guessing everything is fine. Let me check. Give me one. Yeah, we're good. Okay, let's continue with named entity recognition. I'm actually most excited about this particular topic because this is one of those, as I mentioned earlier a couple of times, the application that I'm trying to learn to apply into some of the problems that I see are worth chasing. So let's see how this goes. Let's go.
Neural networks. All good? Any questions? Yes.
What if you have like feature 1 and feature 4? If you multiply them together, it's highly indicative of like the label Y. Can you get to that product relationship through just like multiple layers that are linear?
Yes. Good question. So in conventional stats, you have your basic input features, and when people are building something like a logistic regression model by hand, people often say, well, something that's really important for classification is looking at the pair of feature 4 and feature 7. That, you know, if both of those are true at the same time, something important happens. And so that's referred to normally in stats as an interaction term. And you can by hand add interaction terms to your model. So essentially, a large part of the secret here is having these intermediate layers. They can build interaction terms by themselves. Yeah, so it's sort of automating the search for higher order terms that you want to put into your model. Okay, I'll go on. Other questions? Okay. So here's a brief little interlude on a teeny bit more of NLP, which is sort of a kind of problem we're going to look at for a moment. So this is the task of named entity recognition that I very briefly mentioned last time. So if we have some text, wait, it wasn't appearing to be, okay. Oh. Okay, if we have some text, something that in all sorts of places people want to do is they'd like to find the names of things that are mentioned. And then normally, as well as finding the names of things, you'd actually like to classify them. So you'd like to say some of them are organizations, some of them are people, some of them are places. And so, you know, this has lots of uses. You know, people like to track mentions of companies and people in newspapers and things like that. People, when they do question answering, that a lot of the time the answers to questions are what we call named entities, the names of people, locations, organizations, pop songs, movie names, all of those kind of things are named entities. And if you want to sort of start building up a knowledge base automatically from a lot of text, well, what you normally want to do is get out the named entities and get out relations between them. So this is a common task. So how can we go about doing that? And a common way of doing that is to say, well, we're going to go through the words one at a time, and they're going to be words that are in a context, just like they were for word Devec. And what we're going to do is run a classifier, and we're going to assign them a class. So we're going to say, first word is organization, second word is organization, third word isn't a named entity, fourth word is a person, fifth word is a person, and continue down. So we're running a classification of a word within a position in the text, so it's got surrounding words around it. And so to say what the entities are, many entities are multi-word terms. And so the simplest thing you could imagine doing is just say, well, take the sequence that are all classified the same and call that the entity Shenguofang or something like that. There's a reason why that's slightly defective, and so what people often use is that BIO encoding that I show on the right, but I'm just going to run ahead and not do that now. So it might seem at first that named entity recognition is trivial because, you know, you have company names. Google and Facebook are company names, and whenever you see Google or Facebook, you just say company, and how could you be wrong? But in practice, there's a lot of subtlety, and it's easy to be wrong in named entity recognition. So this is sort of just some of the hard cases. So it's often hard to work out the boundaries of an entity. So in this sentence, First National Bank donates 2 vans to Future School of Fort Smith. So there's presumably the name of a bank there, but is it National Bank and the first is just the first word of a sentence, which is capitalized, you know, like first she ordered some food or something, so kind of unclear what it is. Sometimes it's hard to know whether something's an entity at all. So at the end of this sentence, is Future School the name of some exciting kind of 21st century school, or is it just meaning it's a future school that's going to be built in this town, right? Is it an entity or not at all? Working out the class of an entity is often difficult. So to find out more about Zig Ziglar and read features by, you know, what class is Zig Ziglar? Kind of hard to tell if you don't know. It's actually a person's name. And there are various entities that are ambiguous, right? So Charles Schwab in text is 90% of the time an organization name because there's Charles Schwab Brokerage. But in this particular sentence here, in Woodside, where Larry Ellison and Charles Schwab can live discreetly among wooded estates, that is then a reference to Charles Schwab the person. So there's sort of a fair bit of understanding variously that's needed to get it right. Okay, so what are we going to do with that? And so this suggests what we want to do is build classifiers for language that work inside a context. So, you know, in general, it's not very interesting classifying a word outside a context. We don't actually do that much in NLP. But once you're in a context, it's interesting to do. And named entity recognition is one case. There are lots of other places that comes up. I mean, here's a slightly cool one, that there are some words that can mean themselves and their opposite at the same time, right? So to sanction something can either mean to allow something, or it can mean to punish people who do things, or to seed something can either mean to plant seeds and things, so you're seeding the soil, or it can take seeds out of something like a watermelon, right? You just need to know the context as to which it is. Okay, so that suggests the task that we can classify a word in its context of neighboring words, and NER is an example of that. And the question is, how might we do that? And a very simple way to do it might be to say, well, we have a bunch of words in a row which each have a word vector from something like word to vec. Maybe we could just average those word vectors and then classify the resulting vector. And the problem is that doesn't work very well because you lose position information. You don't actually know anymore which of those word vectors is the one that you're meant to be classifying. So a simple way to do better than that is to say, well, why don't we make a big vector of a word window? So here are words, and they each have a word vector. And so to classify the middle word in a context of here plus or minus 2 words, we're simply going to concatenate these 5 vectors together and say now we have a bigger vector, and let's build a classifier over that vector. So we're classifying this X window, which is then a vector in R5D if we're using d-dimensional word vectors. And we can do that in the kind of way that we did previously, which is that we could say, okay, for that big vector, we're going to learn W weights, and we're going to put it through a softmax classifier, and then we're going to do the decisions. That's a perfectly good way to do things, and for the purpose of what I want to get to in the last part of this is to start looking at my matrix calculus. And we could use this model and do a classifier and learn the weights of it. And indeed, for the handout on the website that we suggest you look at, it does do it with a softmax classifier of precisely this kind. But for the example I do in class, I try to make it a bit simpler. And I want to do this, I think, very quickly because I'm fast running out of time. So one of the famous early papers of neural NLP was this paper by Colbert and Weston, which was first an ICML paper in 2008, which actually just a couple of weeks ago won the ICML 2018 Test of Time Award. And then there's a more recent journal version of it, 2011. And they use this idea of window classification to assign classes like named entities to words in context. But they did it in a slightly different way. So what they said is, well, we've got these windows, and this is one with a location named entity in the middle, and this is one without a location entity in the middle. And so what we want to do is have a system that returns a score, and it should return a high score just as a real number in this case, and it should return a low score if there isn't a location name in the middle of the window in this case. And so explicitly the model just returned a score. And so if you had the top level of your neural network A, and you just then dot product it with a vector U, you then kind of, with that final dot product, you just return a real number. And they used that as the basis of their classifier. So in full glory, what you had is you had this window of words. You looked up a word vector for each word. You then multiplied that. You concatenated the word vectors for the window. You multiplied them by a matrix and added a bias to get a second hidden layer, which is A, and then you multiplied that by a final vector, and that gave you a score for the window, and you wanted the score to be large if it was a location and small if it wasn't a location. So in this sort of pretend example where we have four-dimensional word vectors, that's meaning, for the window, this is a 20 by 1 vector. For calculating the next hidden layer, we've got an 8 by 20 matrix plus a bias vector. Then we've got this sort of 8-dimensional second hidden layer, and then we're computing a final real number. Okay, and so crucially, this is an example of what the question was about. We've put in this extra layer here, right? We could have just said here.
1 second. What I do?
Here's what the question was about.
Review one quick thing. So the x is 20 by 1.
So this is a 20 by 1 vector.
Why is this 20 by 1? 4 per word. Oh, I see. I'm guessing it's x1, x2, x3 plus 1. Yeah. I may be wrong. I don't know. I'll have to assume this for now, and let's see if this gets tested. X is 20 to 1. W is 8 into 20.
For calculating the next hidden layer, we've got an 8 by 20 matrix plus a bias vector. Then we've got this sort of 8-dimensional second hidden layer, and then we're computing a final real number. Okay, and so crucially, this is an example of what the question was about. We've put in this extra layer here, right? We could have just said, here's a word vector, a big word vector of context. Let's just stick a softmax or logistic classification on top to say yes or no for location. But by putting in that extra hidden layer, precisely this extra hidden layer can calculate nonlinear interactions between the input word vectors. So it can calculate things like if the first word is a word like museum and the second word is a word like the preposition in or around, then that's a very good signal that this should be a location in the middle position of the window. So extra layers of a neural network let us calculate these kind of interaction terms between our basic features. Okay. So there's a few more slides here that sort of go through the details of their model, but I'm going to just skip those for now because I'm a little bit behind. And at the end of it, we've just got this.
Let's try to read through these.
Score. So this is our model.
Sorry, yeah. This is okay. Max margin loss. Objective for a single window is the max of 1 minus the score plus score for, oh, is it the context word? Score of the word minus score of the expected context word. I'm not sure, but okay. Yeah, I have to find out what a C is. Each window with an NER location at its center should have a score +1, higher than any window without location at its center. So I think that was the part. I don't know what's going on. My OBS is behaving weirdly today. Give me 1 second, let me fix this. Yeah, all looks good. 1 second, sorry. Yeah, okay. We're back. So each window with an NEI location at its center should have a score +1, higher than any window without a location at its center. Okay. For full objective function, sample several corrupt windows for true one, sum over all training windows, similar to negative sampling in word to vector. Okay. I just look through my negative sampling notes for a second. Okay.
But
Simple net for a score Input. I don't know what h is, or it's just a notation. Was there a slide in between?
I'm going to just skip those for now because I'm a little bit behind, and at the end of it we've just got this score. So this is our model, which is the one that I just outlined, of where we're calculating a score and we're wanting a big score for a location. And so what we're going to want to do is consider how we can use this model to learn our parameters in a neural network. So in particular, remember, it's the same story we had before. We had a loss function j, and we're wanting to work out the gradient with respect to our current theta parameters of the loss function. Then we want to sort of subtract a little multiple of that given by the learning rate from our current parameters to get updated parameters. And if we repeatedly do that in stochastic gradient descent, we'll have better and better parameters which give higher probability to the things that we're actually observing in our training data. And so the thing we want to know is, well, in general, how can we do this differentiation and work out the gradient of our loss function? And so I sort of wanted to the remaining time in this lecture, go through how we can do that by hand using math, and then that'll lead into sort of discussing in more generally the backpropagation algorithm for the next one. Okay, so if we're doing gradients by hand, well, we're doing multivariable calculus, multivariable derivatives. But in particular, normally the most useful way to think about this is as doing matrix calculus, which means we're directly working with vectors and matrices to work out our gradients. And that's normally sort of much faster and more convenient for summarizing our neural network layers than trying to do it in a non-vectorized way. But that doesn't mean that's the only way to do it. If you're sort of confused about what's going on, sometimes thinking it through in a non-vectorized way can be a better way to understand what's going on and make more progress. So like when last time I did the word-to-vec derivatives, when I was writing too small on that board, sorry, that was doing it in a non-vectorized way of working out the weights, talking about them individually. But here we're going to do it with vectors and matrices. And again, look for the lecture notes that cover this material in more detail. In particular, so that no one misses it, let me just clarify what I mean by lecture notes. So if you look at the course syllabus, on the left-hand column, there's the slides that you can download, and straight under the slides it says lecture notes. That's what I'm meaning by the lecture notes.
I think we were looking at these in the beginning of this lecture, like these. I think, yeah, this is it. Yeah, don't worry, I'll link the entire schedule under each of the videos. I'll add them to the previous videos as well, and going forward. But yeah, I mean, there's a lot of stuff, so I'm assuming we may need to do a couple of review classes to go through the earlier versions, and probably will do assignments, but at least do the coded examples. But yep, I think this is what he's talking about.
In the middle column, it then has some readings, and actually there are some different additional things there that cover similar material. They might be helpful as well. But for the thing that's closest to what I'm about to present, it's the lecture notes that appear immediately under the slides link. Okay, so my hope here is the following. If you can't remember how to do single variable calculus, sorry, you're basically sunk and may as well leave now. I'm assuming you know how to do single variable calculus, and I'm assuming you know what a vector and a matrix is. But, you know, I sort of hope that even if you never did multivariable calculus or you can't remember any of it, it's sort of for what we have to do here, not that hard, and you can do it. So here's what you do. Right, so if we have a simple function, f of x equals x cubed, right, its gradient, and so the gradient is the slope, right? It's saying how steep or shallow is the slope of something, and then and also sort of the direction of slope when we go into multiple dimensions. Its gradient is just its derivative, so its derivative is 3x squared. So if you're at the point x equals 3, that, you know, there's sort of this 27 of slopiness, is very steep. Okay, so, well, what if we have a function with one output, but now it has many inputs, so that we're sort of doing that sort of function that was like the dot products, where we're doing the sort of UTV or WTX to calculate a value. Well, then what we're going to calculate is a gradient which is a vector of partial derivatives with respect to each input. So you take the slope of the function as you change x1, the slope of the function as you change x2, through the slope of the function as you changed xn. And each of these you can just calculate as if you were doing single variable calculus, and you just put them all in a vector, and that's then giving you the gradient. And then the gradient in multi-dimensional space is then giving you the direction and slope of a sort of a surface that touches your multi-dimensional f function. Okay, so that's getting a bit scarier, but it gets a little bit scarier than that, because if we have a neural network layer, we then have a function which will have n inputs, which are the input neurons, and it will have m outputs. So if that's the case, you then have a matrix of partial derivatives, which is referred to as the Jacobian. So in the Jacobian, you're sort of taking these partial derivatives with respect to each output along the rows, and with respect to each input down the columns. And so you're getting these m by n partial derivatives, considering every combination of an output and an input. But again, you can fill in every cell of this matrix just by doing single variable calculus, providing you don't get yourself confused. Okay, then we already saw when we were doing...
One second. Too fast for me to jot down everything. But I think this makes sense for all of the n columns and m rows which are individual outputs. I usually get confused between which one's row, which one's column, but I think they should be fine.
Okay. Then we already saw when we were doing Word2Vec that sort of a central tool that we have to use to work out...
Sorry, one quick thing. FJ, yeah. Okay, sorry.
Central tool that we have to use to work out our derivatives of something like a neural network model is we have a sequence of functions that we run one after another. So in a neural network, you're sort of running a sequence of functions one after another. So we have to use the chain rule to work out derivatives when we compose functions. So if we have one variable function, so we have z equals 3y and y equals x squared. If we want to work out the derivative of z with respect to x, we say, aha, that's a composition of two functions. So I use the chain rule, and so that means what I do is I multiply the derivative. So I take dz dy, so that's 2x. Wait, sorry, I said that wrong. Wait, is my example wrong? Oh yeah, wait, dz dy, sorry, dz dy is just 3. That's right, that's the derivative of the top line, and then dy dx is 2x, and I multiply those together, and I get the answer that the derivative of z with respect to x is 6x. Okay, this bit then gets a little bit freakier, but it's true. If you have lots of variables at once, you simply multiply the Jacobians and you get the right answer. So if we're now imagining our neural net, well, sort of this is our typical neural net, right? So we're doing the neural net layer where we have our weight matrix multiplied by our input vector plus the bias, and then we're putting it through a nonlinearity. And then if we want to know what's the partials of h with respect to x, we just say, it's a function composition. So this is easy to do. We work out our first Jacobian, which is the partials of h with respect to z, and then we just multiply it by the partials of z with respect to x, and we get the right answer. Easy. So here's sort of an example Jacobian, which is a sort of a special case that comes up a lot. So it's just good to realize this one, which we'll see with our neural net. So, well, one of the things that we have are these element-wise activation functions. So we have h equals f of z. So what is the partial derivative of h with respect to z? Well, the thing, remember that we sort of apply this element-wise. So we're actually saying hi equals f of zi. So, formally this function has n inputs and n outputs. So its partial derivatives are going to be an n by n Jacobian. But if we think about what's happening there, what we're actually going to find is sort of when we're working out the terms of this, so we're working out how does f of zi change as you change zj, well, if j is not equal to I, it's going to make no difference at all, right? So if my f function is something like putting it through the logistic function or anything else, absolute valuing a number, it's going to make no difference to the calculation of f of zi if I change zj, because it's just not in the equation. And so therefore, the only terms that are actually going to occur and be non-zero are the terms where I equals j. So if we're working out these partial derivatives, if I does not equal j, it's 0. If I does equal j, then we have to work out as single variable calculus what's the derivative of the activation function for. And so this is what our Jacobian looks like for an activation function. It's a diagonal matrix. Everything else is 0, and we've got this activation function. We work out its derivative, and then we calculate that for the different, we have it for the different kind of zi values. Okay, so that's a Jacobians for an activation function. What are the other main cases that we need for a neural network? And these are gone through a little bit more slowly in these same lecture notes. But they're kind of similar to what we saw in the very first class. So if we're wanting to work out the partial derivatives of wx plus b with respect to x, what we get is w. And if we want to work out the partial derivative of wx plus b with respect to b, that means that we get an identity matrix, because b is sort of like a 1b, right? It's this almost always on vector, so you're just getting the 1s coming out to preserve the b. This was the case that we saw when we were doing the word vectors, that if you have a vector dot product of u and h, and you say what's the partial derivatives of that with respect to u, then you get out h transpose. If you haven't seen those before, look at the lecture note handouts and see if you can compute them and they make sense at home. But for the moment, we're going to believe those and use those to see how we can then work out derivatives inside a neural network. Okay. So here's this same neural network we saw before. So we have a window of words, we're looking up word vectors, we're putting it through a hidden layer, and then we're just doing a vector dot product to get this final score. And so what we want to do to be able to train our neural network
Yeah, I'll just quickly jot these down. Try to see if I can compute these. But I think it makes sense for like the identity matrix in case of the derivative with the bias, because it's just going to be 1 for the diagonal, and I'm not sure about the last one. Yeah, we'll have to see.
Derivatives inside a neural network. Okay, so here's this same neural network we saw before. So we have a window of words, we're looking up word vectors, we're putting it through a hidden layer, and then we're just doing a vector dot product to get this final score. And so what we want to do to be able to train our neural network is we want to find out how S changes depending on all the parameters of the model, the X, the W, the B, the U. And so we want to work out partial derivatives of S with respect to each of those, because we can then work out, okay, if you move B up, the score gets better, which is good if it's actually Paris in the middle, and therefore we'll want to nudge up elements of B appropriately. Okay, and so I'm just doing the gradient with respect to the score here, and I skipped over those couple of slides. So if you're just sort of staring at this picture and say, well, how do I work out the partial derivatives of S with respect to B, probably doesn't look obvious. So the first thing that you want to do is sort of break up the equations into simple pieces that compose together, right? So you have the input X, and then that goes into Z equals WX plus B, and then you compose that with the next thing, so H equals F of Z, our activation function, and then this H goes into the next thing of S equals UTH. So we've got these sequence of functions, and pretty much you want to break things up as much as you can. I mean, I could have broken this up even further. I could have said Z1 equals WX, Z equals Z1 plus B. It turns out that if you've just got things added and subtracted, you can sort of do that in one step, because the sort of pathways separate in when doing the derivatives, but sort of anything else that composes together, you want to pull it out for the pieces. Okay, so now our neural net is doing a sequence of function compositions. And when we say, okay, we know how to do that, the chain rule, so if we want to work out the partials of S with respect to B, it's just going to be the product of the derivatives of each step along the way. So it's going to be the partial of S with respect to H times H with respect to Z times Z with respect to B, and that will give us the right answer. So then all we have to do is actually compute that. So I think this just sort of shows, okay, we're taking the partials for each step of that composition. Okay, so now we want to compute that. And so this is where I'm going to sort of use the Jacobians that I sort of asserted without much proof on the preceding slide. Okay, so first of all, we have ds dh. Well, that's the dot product of two vectors. So the Jacobian for that is just H transpose. Okay, that's a start. Then we have H equals f of z. Well, that's the activation function. So the Jacobian of that is this diagonal matrix made of the element-wise derivative of the function f. And then we have the partial of z with respect to b, and that's the bit that comes out as the identity matrix. And so that's then giving us our calculation of the partial of s with respect to b. And so we can see that the identity matrix sort of goes away, so we end up with this composition of ht times f prime of z. Okay, suppose we then want to go on and compute now the with this. Then want to go on and compute now the partial of s with respect to w. Well, our starting off point is exactly the same chain rule that we work out each of the stages. So that first of all, you're working out the z from the wx part, then putting it through the nonlinearity, then doing the dot product of the vectors. So that part is the same. And what you should notice is that if you compare the partial of s with respect to w versus s with respect to b, most of them are the same, and it's only the part at the end that's different. And that sort of makes sense in terms of our neural net, right? That when we had our neural net, that the W and the B were coming in here, and once you've sort of done some stuff with them, you're putting things through the same activation function and doing the same dot product to create a score. So you're sort of doing the same calculations that you're then composing with. So it sort of makes sense that you should be getting the same derivatives that are same partial derivatives that are occurring at that point. And so effectively, you know, these partial derivatives correspond to the computations in the neural network that are above where W and B are. And so those are commonly referred to as delta. Note delta, which is different from partial derivative d. And so delta is referred to as the error signal in neural network talk. So it's what you're calculating as the partial derivatives above the parameters that you're working out the partial derivatives with respect to. So a lot of the secret, as we'll see next time, a lot of the secret of what happens with backpropagation is just we want to do efficient computation in the sort of way that computer science people like to do efficient computation. And so precisely what we want to notice is that there is one error signal that comes from above, and we want to compute it once and then reuse it when calculating both partial derivatives with respect to W and with B. Okay, so there's sort of two things to still do. So one is, well, it'd be kind of useful to know what the partial derivative of s with respect to w actually looks like. I mean, is that a number, a vector, a matrix, a three-dimensional tensor? And then we actually want to work out its values. And to work out its values, we're going to still have to work out the partial derivative of z with respect to w. But if first of all we just try and work out its shape, what kind of shape does it have? And this is actually sort of a bit tricky and is sort of a dirty underbelly of doing this kind of matrix calculus. So since our weight vector is an n by m matrix, the end result of the partial of S with respect to W is we have a function with n times m inputs, all of the elements of W, and simply one output, which is our score. So that makes it sound like, according to what I said before, we should have a 1 by n times m Jacobian. But it turns out that's not really what we want, right? Because what we wanted to do is use what we calculate inside this stochastic gradient descent update algorithm. And if we're doing this, we'd sort of like to have the old weight matrix, and we'd like to subtract a bit from it to get a new weight matrix. So it'd be kind of nice if the shape of our Jacobian was the same shape as W. And so we and in general, what you always want to do with neural nets is follow what we call the shape convention, which is we're going to sort of represent the Jacobian so it's in the same shape as the inputs. And this whole thing is kind of the bad part of doing matrix calculus. Like, there's a lot of inconsistency as to how people represent matrix calculus, that in general, if you just go to different fields like economics and physics, some people use a numerator convention, some people use a denominator convention. We're using neither of those. We're going to use this shape convention, so we match the shape of the input, so it makes it easy to do our weight updates. Okay, input, so it makes it easy to do our weight updates. Okay, so that's what we want the answer to look like. So then the final thing we need to do to work out the partial of S with respect to W is we have the error signal delta that's going to be part of the answer, and then we want to work out the partial of Z with respect to W. What's that going to be? Well, it turns out, and I'm about to be saved by the bell here since I'm down to 2 minutes left. It turns out that what we end up with for that is we take the product of the product of delta times x. So effectively, we've got the local error signal above W, and then we have the inputs x, and we're working out an outer product of them. And
The issue is the professor is rushing through these slides, and I don't want to just rush through these, trying to understand as best as I can. The delta is going to be in the answer, that's right, okay. We calculated that. The other term should be x, because C is a function of x, yes. So it turns out, how does that turn out?
And we're working out an outer product
By the transposes, okay, in by m. Is that because of the convention?
of them. And we're working out an outer product of them. And the sort of way to think about this is sort of for the W's, we've got the elements of the W matrix are these different connections between our neurons. And so each one of these is connecting one output to one input. And so we're going to be sort of making this n by m matrix of our partial derivatives that are going to be the product of the error signal for the appropriate output multiplied by our input, and those give us the partial derivatives. I'm skipping ahead quickly in my last 1 minute. Okay, so right, so this is sort of what I said. I've used the shape convention. I'm going to skip that. Okay, so I ran out of time a teeny bit at the end, but I mean, I think hopefully that's conveyed most of the idea of how you can sort of use the chain rule and work out the derivatives and work them out in terms of these vector and matrix derivatives. And essentially what we want to do for backpropagation is to say, how could we get a computer to do this automatically for us and to do it efficiently? And that's what sort of the deep learning frameworks like TensorFlow and PyTorch do, and how you can do that we'll look at more next time.
Yeah, it was a bit rushed at the end. I just want to read through these slides again. So, okay, this was fine because again, whatever the convention was, we have the delta transpose multiplied by x transpose. Okay, so that's the local error signal, local input signal.
Those give us the partial derivatives.
Yes, we calculate that this is the delta, but the convention says the gradient should be a column vector because B is a column vector. Yes? Yeah, that's the shape convention. Disagreement between Jacobian form, which makes chain rule easy, and the shape convention, which makes the implementing SGD easy. They expect answers to follow the shape convention, but Jacobian form is easier for computing errors. Oh, okay. I think what you're trying to say is like they are sort of two different things running together. So there's going to be a disagreement, but because I think algebraically, that's the word, delta is a row vector, but convention says the gradient should be a column vector because B is a column vector, which is not the case. So I think we're doing a little bit of cheating here.
I'm skipping ahead quickly in my last 1 minute. Okay, so right, so this is sort of what I said. I've used the shape.
Two options. One, use Jacobian form as much as possible. Reshape follow convention at the end. Okay, what we just did here. But at the end, transpose is to make a derivative a column vector resulting in delta. Okay, done. This makes sense. Up until calculation of the delta, use the normal algebraic math. And number two is always follow the convention. Look at the dimensions to figure out when to transpose and or reorder terms. Yeah, no, I don't want to confuse. Number one, that's the way to go.
Convention. I'm going to skip that.
Okay,
okay, so
yeah. Next class, I think will be more hands-on from an algorithmic and coding standpoint. So should be interesting. Today was a little heavy. We even heavy also on time. We are at the 1 hour 50 minute mark almost. But I think today's class was, I mean, even if it was more computational hand by hand oriented, but still an interesting class. I actually understood a lot of the stuff, so I'm a little happier than I would say the previous class. I'll see if we can do a couple of, maybe like a review session every 2 weeks or something like that. That's what I was just thinking of, but more to follow. I'm not sure how this lands up. So yeah, I will link the course uh, page that the professor had mentioned multiple times. As I said, on every videos, I'll add to the previous ones, the forthcoming videos as well. But with that, I think we are done for today. So thank you so much for watching. Please subscribe, hit that notification bell. The idea is to create a sense of discipline, so that obviously me personally, to create a sense of discipline so that I'm able to learn all of these things that I've been procrastinating for, I would say, the past, I don't know how many years, if not months. But at the same time also keep accountable, or keep accountability across the board. If you guys are involved with me, I will keep you accountable, and I think just this platform virtually is keeping me accountable. We can very happy to be tagging along on that front. I don't know, the stream's lagging again, but maybe a signal to end the stream because it's been going on for too long. But today is actually Christmas, so Merry Christmas. Have a great day today, and I will see you tomorrow. Take care. Bye.